Welcome back. So, let us continue from where we left off. At the end of the last lecture, I was talking about a problem. I was discussing a problem on the two-step binomial model. So, let us revisit that problem and then we will proceed therefrom. Consider a 2-year European put with a strike price of 52 on a stock whose current price is 50. In each time step of 1 year, the stock price either moves up by 20% or moves down by 20%. Let the risk free interest rate be 5% per annum continuously compounded. Calculate the current price of the option using a two-step binomial model. So, the data that is given to us is the current stock price at the up and down swings are given in terms of percentages. The life of the option is 2 years and we have to model it as a two-step binomial tree, and the risk free rate is also given as 5% per annum continuously compounded. So, our first step is to work out the synthetic probabilities. Please note, because the size of the up jump and the down jump is the same across the entire tree, the synthetic probabilities or the Q probabilities corresponding to the different branches of the tree will be the same, and we can work them out as Q of u is equal to S0 e to the power R t minus S t upon S u minus S t, or in terms of percentages of price changes, size of jumps in terms of percentages, if I divide throughout by S0, what I get is e to the power R t minus d divided by u minus d. So, this is the formula that we use for q u. Q d will be equal to 1 minus q u, as you all know, and the rest of the, then we also need of course to calculate the value of the option at the various terminal nodes. Now, if the stock price at maturity turns out to be 72, then the put option will not be exercised and therefore, the value of the option will be 0. If the stock price turns out to be 48, the put option will be exercised and the payoff is equal to k minus s t, that is 52 minus 48, that is 4, and if the stock price turns out to be 32, then the payoff from the option will be equal to 52 minus 32, that is 20. These are the figures that are given in the adjoining the nodal points D, E and F. Now, the first step is to work backwards. For example, we can work backwards for this branch of the tree or this segment of the tree, and what we arrive at is that the value of the option at the node B, it turns out to be 1.4147. Similarly, using the data that we have for this branch of this option or this segment of the tree, I am sorry, what we get is f d is equal to 9.4636. For example, we can work out f u as e to the power minus r t q u f u u plus q d f u d. Now, putting in the various values q u and q d, we have already worked out. F u u for this segment of the tree is 0 and f u d is equal to 4, r is equal to 5% continuously compounded, t is equal to 1 year, and that enables us to work out f u. Similarly, we can work out f t, and using f u and f t and again the same values of q u and q d, we can work out the value of t equal to 0, which turns out to be 4.1923. So, this is the working of this example. We work out the risk neutral probabilities. Q u turns out to be 0.6282 and q d is 0.3718. The stock prices at the various nodes are easily worked out. You are given that the current stock price is 50, that t equal to 1 jump is either 20% upwards or 20% downwards. So, it would either be 60 or it would be 40, and then there is another jump at t equal to 2, which would again be of 20% upwards or 20% downwards. So, the possible or the spectrum of prices at t equal to 2 would be would be 72, would be 48 and then 32. That is what is given here. SUU is 72, SUD is equal to 48, SDD is equal to 32. And please note here one thing, that SUD is equal to SDU, that is equal to 48. This is called a concomitant tree. A tree where the branches recombine is called a recombinant tree. I am sorry. So, please note this particular feature of this type of binomial tree. SDD is equal to 32, SU is equal to 60, SD is equal to 40 and S0 is equal to 50. Claim values I have already explained at the various nodes. It is 0 for the upper node when the stock price is 72, 4 for the middle node when the stock price is 48 and the claim value is 20 for the lower node when the stock price is 32. Then this is the working for FU, as I explained, FU is given by e to the power minus RT Q into FUU plus 1 QD, that is 1 minus QU into FUD. Substituting the various values, we get the value of FUU as 1.4147. Similarly, FD is 9.4636, and using these two values then and working backwards, we get the value of F0 as 4.1923. So, in essence, we are rolling back the tree from the terminal, from the data that is there at the terminal node, we roll back the tree step by step and then we arrive at the value at t equal to 0, which is F0. Now, we modify this methodology to work out the value of an American option. Recall that what is the difference between the American and the European option. The European option is exercisable only at maturity. For example, in the option that we just considered, the maturity of the option was 2 years. So, the option could only be exercised at t equal to 2 years and not earlier. However, in the case of American option, the option holder has the discretion, has the choice to exercise the option at an earlier date as well. Now, the implication of this property on the methodology that I have just discussed is that we need to examine at every node whether the option exercise would be optimal or not. In other words, whether the payoff generated from the exercise of the option is higher than the computed value of the option, and if the payoff generated from the exercise of the option is higher, we will substitute that higher value at that particular node in the tree. Why? Because the logic is simple. The logic is that if the exercise of the option, which is now allowed because it is American and results in a higher payoff, the investor would exercise the option and claim the higher payoff rather than the implicit the intrinsic value of the option, which is the calculated value as per the binomial tree. So, let me repeat, when we are evaluating a American option using the same binomial tree methodology, the only difference will be that at every node we need to check whether the exercise of the option gives you a higher payoff than the computed value, and if it so happens that at any particular node that the exercise of the option gives you a higher payoff than the computed value, then we will substitute that higher payoff for the computed value and proceed as earlier, working backwards until we arrive at the value at t equal to 0. Even at t equal to 0, we will check whether the early exercise of the option at t equal to 0 or the immediate exercise of the option gives you a higher payoff than the payoff that is represented in terms of the backward calculation of the binomial tree. So, let us as an illustration, let us do the same problem that we did just now on the premise that the underlying put option is a American put. So, we consider a 2-year American put. Now, please note this particular feature. American put with a strike price of 52 on a stock whose current price is 50 in each time step of 1 year. This is a 2-year put. So, we are having a 2-step binomial tree model just as in the previous case. In each time step of 1 year, the stock price either moves up by 20% or moves down by 20%. The risk free interest rate is 5% per annum continuously compounded. Calculate the current price of the option. Now, this is what we calculated in the previous example. These were the stock values in red at the terminal nodes, and corresponding to these stock values, because it is a put option, the payoffs were given at the node D by 0, because the recall that the exercise price is 52, k is equal to 52. So, if the stock price is higher than the exercise price, the output will not be exercised and the payoff will be 0. At this point, because k is 52, the stock price is 48, the option will be exercised, yielding a payoff of 4, and similarly the payoff at the point f will be 20. Now, using this data and using q u and q d, if you recall, is equal to 0.6282 and 0.3718. These are the values of the probabilities, and these are the same across the various segments of the tree on the because of the reason that u and d, that is the percentage up jump and the percentage down jump, are same in each case. Right. Using this q u and q d and f u u and f u d, we arrive at this value 1.4147. Now, at the node B, we need to check whether the put option exercise will give you a higher payoff than the computed value, which is 1.4147. The stock price is 60, the exercise price, please note, is 52. So, obviously, if you exercise the option, you will get a 0 payoff, because recall it is a put option, and the computed value is 1.4147, which is higher, and therefore, we will carry backward the computed value. We will ignore the value or the payoff that is arising out of the exercise of the option, because it results in a lower payoff. In this case, it is a 0 payoff. Now, let us look at the other scenario represented at the node C. The computed value at the node C, using the same formula as we have here, is 9.4636. The price of the stock at this point is 40, the exercise price is 52. Therefore, if I exercise the option at the node C, I will get a payoff of 12. The computed value is 9.4636. So, obviously, at this point at the node C, it is optimal to exercise the option. Should the system evolve in such a way that node C materializes, I would be better off exercising the option at this node rather than carrying it forward for the next year, for the second year. So, I should exercise the option at the end of the first year if the stock price goes down to 40, because I will get a payoff of 12 in distinction to the value of the option at this node, which is given by 9.4636. So, what we do is we substitute this 12 figure instead of this 9.4636 when we work out the value of the option at t equal to 0 or at the point at the initial node. I repeat, instead of 9.4636, we shall use 12 when we calculate the value of the option at the node A. If you, therefore, what will be the values? Q u and q d will be the same, of course, and f u will be equal to 1.4147 and f d will be equal to 12.0000, and therefore, we will arrive at f 0 is equal to e to the power minus r t, that is minus 0.05 into 1 into q u, that is 0.3718 into f u, and that is 1.4147 plus 0.3718. I am sorry, this is 0.6282 into 1.4147 plus 0.3718 into 12.00. So, this will be the value, and this will be equal to 5.08. Now, please note this change in value. In the case of the European option, the value was 4.19. Here we are arriving at a value of 5.08. So, this is the working. These are the stock values at the various nodes, and these are the claim values at the terminal nodes. This is the working backwards, as you can see here. F u is equal to this expression which is FU is equal to 1.4147, but FU early exercise is equal to 0 because the stock price is equal to at the point B, the stock price is equal to 60 and the exercise price is 52. So, the option will not be exercised. So, the early exercise value is 0. Therefore, the maximum of this maximum of A and B, that is the computed value and the payoff, is equal to 1.4147. Then we talk about F D. The computed value at F D is 9.4636. The exercise value is equal to 12. And in this case, you can see here that the computed value is lower, the payoff is higher, and therefore, for the next step we will carry the value of F D as 12 and not as 9.4636. So, this is shown here. This is replaced, 9.4636 is replaced by 12 and 4.1923 is replaced by 5.0894. So, this is how we work, and please note, finally, we also check for early exercise at t equal to 0, that is at the node A. Now, at the node A, the stock price is equal to 50, the exercise price is 52, therefore, the payoff from the option is only 2. However, the price of the option turns out to be 5.0894, therefore, we will go along with the computed value of the option at node A, that is 5.0894, which will represent the worth of the option, which will represent the price of the option. So, at every node we need to check for early exercise. If on early exercise, is it beneficial, is it more beneficial to the investor, to the party holding the long position, and if it so happens that the payoff is higher compared to the computed value, we replace the computed value by the payoff, which is the higher value, and we work as earlier. Now, we move from the binomial model to the continuous time model, the continuous variable model, which is the celebrated Black-Scholes model, which was propounded by Fisher Black and Myron-Scholes, for which they were awarded the Nobel Prize as well. So, we shall, but before we get into this model, we work out the Black-Scholes partial differential equation, the solution of which gives us the value of the derivative. We need to introduce certain concepts, and we need to follow a certain stepwise methodology, which is explained or which is specified in this particular slide. We start with explaining the concept of Brownian motion, we generalize the concept of Brownian motion, and then we derive or we obtain the Ito's equation. Our next step is to work to model the stock price, because you see we cannot arrive at the value of the option unless we have some model for the behavior of the stock price. So, the next step is to model the stock price, and then we will show that the assumptions that go into the modeling of the stock price imply that the stock price will follow a log normal distribution. Our next step would be to derive the Black-Scholes partial differential equation. We will also talk about, you see, the one thing is, let me clarify that the Black-Scholes partial differential equations derivation follows the same methodology or same philosophy as the no arbitrage principle in the one step or two step binomial model. However, we also saw in the context of the binomial model that the no arbitrage or the arbitrage free binomial model is similar to or is equivalent to the risk neutral valuation of the underlying option, and we will also do the risk neutral valuation of the option using the same methodology as we did for in the case of the binomial model. So, without much ado, let us proceed to the first step. Let us now move to the discussion on Brownian motion. Before that, you see, why do we need all that? You see, that is explained in the slide very succinctly. This is our objective. This is our objective. What is our objective? Our objective is to ascribe a price to derivative securities. Now, derivative securities, what are derivative securities? They are functions, or their prices are functions of prices of the underlying assets. Therefore, we need to have a model for the prices of underlying assets, and the underlying assets have a content of randomness in their prices. As I mentioned once during this course of this lecture series, that we need necessarily to have some element of randomness in the behavior of the underlying assets, the price of the underlying assets, if we are to construct derivative securities or derivative instruments on those assets, and if the derivative instruments are to be worthwhile, are to be useful. Otherwise, if the behavior of the underlying asset is deterministic, if it is absolutely known how the system or how the asset is going to evolve over the future, there is no point in writing derivative contracts on such instruments. Therefore, the underlying assets that we have in practice on which derivative contracts are written are invariably assets whose evolution is embedded with a certain amount of randomness, and such processes which are not perfectly predictable, or whose future evolution is not perfectly predictable, they have an element of randomness in their evolution, are called stochastic processes. So, prices of derivatives are functions of prices of underlying assets, which are stochastic processes. So, a quick touch on the types of evolution of processes. First of all, the simplest is the deterministic processes, where given a knowledge about the initial conditions of the process, we are able to precisely predict the future evolution of the process with perfect precision. That is the important part. So, given the knowledge of the initial conditions, the t equal to 0 status of the process, we can precisely predict the future evolution of the process. These are called deterministic processes. So, let me read it out for you. Processes that evolve in time in a precisely predictable manner are called deterministic processes. In such processes, knowledge of the state of the system at any given point in time enables us to precisely predict a state at a future point in time. So, there is no randomness in their behavior. If you know their status, if you know their cardinals at a given point in time, let us say arbitrarily that you know the cardinals of the process at t equal to 0, then you can precisely predict how the process is going to evolve over the future time period for which the experiment or observation is to be made. A system will be deterministic if we have full knowledge of the state of the system at a given point in time, arbitrarily t equal to 0, not necessarily so, but usually we have it as t equal to 0. It can be any arbitrary point in time, and knowing that the status of the process at any arbitrary point in time, we are able to precisely predict the behavior of the system thereafter. That is the important thing, and therefore, we have full knowledge of the state of the system at a given point in time, the state vector, and we have knowledge of the evolutionary dynamics of the state vector in time. So, how the state vector or how the system is going to evolve in time, what are the physical laws, the financial laws, or other laws that the system is going to obey as it evolves in time, we have knowledge about that, and we have the initial conditions known to us. If you have information on both of these, then we can precisely predict, and the system would be deterministic. Then we have a stochastic process. A stochastic process is a process that evolves in time in a random manner. There is an element of randomness in its evolution. Therefore, what is the important characteristic of a stochastic process? The important characteristic of a stochastic process is that its evolution or its trajectory cannot be precisely ascertained, cannot be precisely determined, knowing its initial conditions at t equal to 0. How it is going to evolve in future, we do not know with absolute certainty. We encountered an example just in the last lecture when we talked about the binomial model. At t equal to capital T, that was at t equal to one time step, the underlying asset could either jump up to SU or it could jump down to SD, but whether it is going to jump up or down is not known to me sitting here at t equal to 0. That is, the evolution is random. We do not know what value it is going to take at t equal to capital T when it is going to undergo a transition. So, a stochastic process is a process that evolves in time in a random manner. Thus, it can be represented by a sequence of random variables indexed with reference to the instance of time at which the process evolves. Just as we did in the binomial model, at t equal to capital T, the stock price, let us say the stock price could either go up to SU or could either go down to ST. Now, this is thus we can model the behavior of the stock price at t equal to capital T by a random variable ST, where ST can take the value SU or it can take the value ST with certain well defined probabilities. So, this is called a random variable. ST is the random variable and SU and S2 are the possible values that the random variable could take with of course, the respective probabilities whatever they may be. We can thus now this was a single step model. This was a model where the system or the stock underwent a transition only at one point in time, and if we have a two step model, then we can model it using two random variables, one random variable to capture the jump at t equal to 1 and the second random variable to capture the jump at t equal to 2. So, if it is an n step process, then we need n random variables and the entire process can be represented or can be collectively known as the sequence of random variables S1, S2, S3 and so on. So, we can thus represent a stochastic process as a sequence ST t greater than equal to 0 of random variables defined on a suitable probability space. That means, we can ascribe appropriate well defined probabilities to each of those random variables that constitute the stochastic process. This is an illustration at t equal to 1, we have the random variable a could take certain values. At t equal to 2 was again when the system undergoes a transition, we have we can represent it by the random variable b can again have a spectrum of values with respective probabilities. You see, please note, we are sitting here at t equal to 0, all this is at t, this is, let us say this is t equal to 0. So, at t equal to 0, we want to forecast or we want to predict or we want to study the behavior of the system as it evolves over time from t equal to 0 onwards. The system can make transitions at t equal to 1, t equal to 2, t equal to 3 and so on. And at each point at which the system can make a transition, it can take one of the values of a spectrum of values, and therefore, we can represent it by a single random variable at that particular point in time. Similarly, at t equal to 2, again the system will undergo a transition. So, we need another random variable to describe the behavior of the system or the jumps of the system at t equal to 2 and so on. So, this collection of random variables a, b, c, d, e and f, these will constitute this stochastic process that we are trying to study. We can represent a stochastic process as a sequence of random variables x t, t contained in I, defined on a suitable probability space. The index at I, which usually represents time, not necessarily so, but usually it represents time, and it can either be discrete or continuous. Discrete, therefore, we can have discrete time processes and continuous time processes. Talking briefly about discrete time processes, stochastic processes usually evolve with time. They are therefore indexed with reference to points on the timeline. In discrete time processes, the process evolves, undergoes a transition at discretely identified points on the timeline. Please note the timeline itself may be continuous. There is no restriction on the timeline not being continuous. The point is that the system will evolve, the system will undergo a transition at discrete points on the timeline, discrete well defined points on the timeline at which the system will evolve, the system will undergo a transition. So, in discrete time processes, and these are called time steps by the way, at which the system undergoes a transition. In discrete time processes, the process evolves, undergoes a transition in discretely identified points on the timeline. Thus, from the perspective of the process, time is assumed to evolve in discontinuous jumps. This is the important part. From the perspective of the system, because it is only going to make a transition at discrete points. So, if you look at it from the perspective of the system, time is not flowing continuously, time is flowing in jumps, time is flowing in discrete chunks, and at every jump the system wakes up and makes a transition. Then when the next jump occurs, the system again wakes up and makes a transition. So, these are discrete time processes. So, thus from the perspective of the process, time is assumed to evolve in continuous jumps, that is in discrete steps of a certain length. Discrete time can be represented by a lattice with lattice points labeled by integers. Now, timeline versus time steps, I have emphasized this point already. Timeline is the underlying continuous flow of time. However, on the timeline you can have discrete points at which the system undergoes a transition, and these are called time steps. This will be one time step, this will be two time steps, and so on. So, the time steps are those discrete points on the timeline, usually spaced equidistant apart, at which the state of the observed system undergoes a transition. Thus, from the system's perspective, time evolves in discontinuous jumps. Then we have discrete variable processes. In discrete variable processes, the random variables comprising the stochastic processes map to a discrete set. In other words, simply stated, the random variables which form the sequence of which forms the stochastic processes have a discrete spectrum of possible values. They cannot take any value within a continuous interval or a continuous set. They can take only discrete values within a set of possible values. So, that is a discrete variable process, that is the random variables forming the stochastic processes are discrete. Discrete variables can be represented by a lattice with lattice point labeled by integers. Then we talk about Markov processes quickly. Markov processes are those processes whose memory is confined to the preceding state alone. For example, if you look at the future evolution of a particular process, the present state of a particular system, the evolution of the present state of the particular system will depend only on where the system was at the previous state and not earlier. How the system reached that previous state is irrelevant. What path or what is the sequence of random values that the random variables took, what path the system followed in arriving at this particular point is irrelevant. It is only if you are studying the value of the process at t equal to 1, then the value of the process at t equal to 0 is the only criterion that will determine which of the possible values the system could take at t equal to 1. So, that is a Markov process, a process whose memory is confined to the immediately preceding value. So, let me quickly read it out. For a Markov process, we can say that the future state of the process is dependent only on its present state and not on the history of how the process reached the present state. This is important. The path is irrelevant. The path is irrelevant. The path followed by the system thus far is irrelevant. It is only the current value which is relevant for knowing which of the following possible values the system could take in the next step. Its memory is restricted at any instant of time to the immediately preceding time argument alone. So, what it is going to do at t equal to 1 will depend on where it is at t equal to 0 and not earlier That is, the current evolution of a Markov process depends only on its immediately preceding state and no earlier states. One step unbiased random walk will take it up after the break. Thank you.